We have an exciting session coming up, and I'm very happy to welcome our next two speakers. We will be moderating the session together with Professor Arno Schmidt-Truxes. And our first speaker is Yannis Pitsiladis. Yannis, it's a great pleasure to be welcoming you to Lausanne. You do come to Lausanne regularly because you are on the executive committee of FIMS, which is based in Lausanne, so the Fédération Internationale Médecine du Sport. And you also are present on the executive boards, I think, of EFSMA, and as well as the ROC Medical Commission. So you're not a foreigner in Lausanne, if I may say so. Having said that, you did come from Hong Kong. This is where you currently work, but you're used to traveling a lot over the years in the wide range of domains that you have been active, and from genetics to human performance and physiology, all of these aspects. So it's exciting to hear you talk about genetics versus lifestyle training for health and performance. Yannis, the floor is yours.
Thank you, Boris, for the invitation, for that nice introduction. And I'd like to also thank you all. I was quite delighted when I was given this title. As you heard from the introduction there was quite a lot of different things I could talk about. But I believe this topic, and I want to congratulate the organizing committee for putting this topic on the program. I'm going to say something that will probably receive not necessarily the right way. I would like to contend that this is the most important topic on your conference program. And if I can't convince you by the end of my 20 minutes, then I failed miserably. Okay, so let me try and convince you about that as I go through my presentation. And again, thank you to the organizing committee. I've really enjoyed my stay. I also felt very compelled, given the fact that now I'm based in Hong Kong, with input also into mainland China, to actually give you an update where we are in this field today. Again, to try and convince you that this is the most important topic on the program in terms of also your clinical work, because I know who the audience is. And when I looked at the program, and I attended quite a lot of the program, there was a few times mention of genetics, but there was nothing else. So again, I want to try and convince the organizing committee for next year or the year after especially to have symposia on this topic, and you'll see why. So having just come from Huanzhou in China, where some of the world's experts on this topic got together, I've put together this talk based on the very best state-of-the-art of what was going on to try and, again, influence you as you move forward in this field, hopefully, as well. Now, as someone who speaks at conferences quite often, you never try and give a 50-minute lecture in 20 minutes. But I felt to convince you, I'm going to have to talk about all the aspects that I think are important, so I'm going to have to go a little bit fast. But today's aim is to give you a flavor of what you are missing and what every single one of you in this room has to start doubling with to a certain extent, even possibly a great extent. So this is roughly what I'm going to talk about in the time I have. And starting off the first one, which is the genetic foundations of performance, it's really to convince you that most of the phenotypes of our interest, whether it's your rehabilitation, whether it's you trying to diagnose a patient's condition, genetics is absolutely key, and also in terms of performance. And let me try and convince you of that in the next few slides. And for those of you who, probably most of you not in the field, there's also a history of sports genetics in this text, which is a bit old now, but it still gives you the history of the field, which I think is quite important. And the history goes right back to Hippocrates. So this field is 2,500 years old. I'm not going to read all that, but I've underlined one word that's important, which is predisposition. Hippocrates was the first person to actually convince us, even in that statement, which will be relevant and valuable today, that predisposition is so important. In other words, hereditary or genetics. He couldn't quantify it, but he knew it was important. And again, if you read all that, I'm sure you'll be impressed because it incorporates everything that's important. But the next real quantification, because others like Francis Galton talked about, again, the importance of hereditary, but the first person to really put a number to it was Vasilis Klisouras, who happened to be at the meeting I've just come from in mainland China. And what he did in the 1970s, because at that point he couldn't measure the genes per se, he used a twin study approach, comparing identical twins to non-identical twins and looking at a variety of phenotypes, particular VO2 max, the anaerobic performance, as well as also maximum heart rate. And what you can see on the slide very clearly in solid circles, the monozygotic twins, the ones who basically have identical genome, are very closely correlated in terms of those phenotypes. While the dizygotic twins, which are based like any other siblings, are not. And the numbers that he comes up with on the top right, as you can see here, this is not a pointer, so I can't point it, but you can see the numbers there, over 90%. That tells you what a lot of you know, that if you measure someone's VO2 max and it's 50 and they want to become 70 or 80, it's just not possible. It's not going to happen. And then others, like Claude Bouchard, heard that message and did the same thing with something that may be even more important for you, which is the trainability. And he demonstrated the same thing there. You can see the R correlation there of 0.74, so approximately 74% of trainability has this genetic component. Very, very important. And fortunately, it's not 100% because then you have no job to do. The training, the rehabilitation, etc. But you can see such a powerful genetic component. And then he went on to do, well, before he went on to do the study, which a lot of you will know, the heritage family study, Hugh Montgomery and others started a candidate gene approach where the first genes were being looked at, but one gene at a time, which, as I'll show you, is not that helpful as we think of it today. But he did, Bouchard, this particular study where he again quantified, and in this particular study, which I think a lot of you will be aware of, everyone had to do 20 weeks of training, exactly the same, exact same conditions. You can see the responses. The average improvement was about 300 mils per minute. But if you look at the individual improvements of the different families, you'll see some improved by over a liter, dramatic improvement within that family, and others, interestingly, got worse. And if you think back to the presentations you've heard, the ones like I heard as well, where average data is being presented, imagine how wrong you will get, and why sometimes the interventions are not coming out to be validated because some are improving and some are not improving. But the problem is you don't know which ones are which. And that's why I'm trying to convince you that you're missing that individual response, as you can see here. And you can see the maximum heritability there comes out to about 50%, a bit lower than what it showed in the twin study approach. And it shows very nicely that there's 2 times more variance between families than within families. Again, showing us the first bit, that the blueprint is very important. And again, I don't have time, but I'm often asked, what about skill, motor learning, or motor control? Again, Vasilis Klisouras some years later did a similar study using the same paradigm, the twin studies, and looking at a very basic movement, which is abduction of the thumb. And he finds, without going into the details, heritability estimate of how much do you think? Around about 70%. So even skill and learning of a skill has this high genetic component. And you can see on the top there the difference between the monozygotic and the dizygotic in terms of motor control and motor learning, that the dizygotic twins, the learning and the control is very similar versus very diverse in the dizygotic twins. Again, confirming what I said to you earlier on. And you can see a lot of these phenotypes, which are things that you measure, that you are interested in, have again a very high heritability estimate. And yes, in one of the talks where someone did mention genetics, and there's a slide on the top left if you remember about genetics, and it was about lower back pain, let me ask you, because lower back pain is not up there. What do you think is the heritability estimate of lower back pain, which is what you are interested in? Anyone know? Give me a number. Throw out a number from 0 to 100. Well, I'll help you. It ranges from twin studies anywhere between 21 and 67%. So when you have 67%, you can imagine what you're missing. So you, in your clinics and in your work that you're doing every day, are missing all of this. So you're only working on the 30%. I'm being very simplistic in what I'm saying. That's why I'm saying to you this is so very important. And Vasilis Christos goes on to do the twin study of Olympic champions. And these are two identical twins, Italian race walkers. The one does exceptionally well, medals 3 times at Olympics. The other one still becomes a good athlete, but nowhere near as great as his brother. So the point I want to make with this slide, and they're the brothers, and what they achieved, is that genes are not destiny, however. So don't worry, you're not going to be out of a job, because what you do is still very important, but within the blueprint, the constraints of that blueprint. And that's what this study beautifully shows us. And again, I don't have time to go into details here, but what differentiated these twins was on the psychological component of performance. One of the twins, who actually was the better one in performance, would get really offended when he was being criticized. And the data clearly showed that. But again, I don't have time to go through this. Okay, so that's my first section done, and we look at the time. Okay, wow, I'm already halfway. Whew, speed up. Okay, so the first bit was to show you about performance. The second one is about, okay, I already mentioned that there's 1, 2 genes that are not going to work. We needed something else. And going back to the 1990s, the Human Genome Project, I, like some of you, said, okay, soon, once this finishes, we're going to be able to identify who's going to respond, identify the performance of athletes beforehand, do genetic testing for talent ID, etc. None of this has happened, okay? None of it has happened, and why? And if you look at this slide, it shows you the different chromosomes. On every chromosome here, you'll see a dot. A dot relates to a study showing an association, some important traits. And on the right-hand side, you can see traits that you are interested in. And there are thousands of papers published on what genes are doing what. So clearly, these genes are important. And what the Human Genome Project taught us, and I'm not saying it was a waste of time, the opposite, but it didn't do what some of us were hoping, but it allowed us to understand how complex this issue is. And again, I'd love to go through all of this, but I don't have time, so I'm just going to stress a few things. There are about 40 million common variants. So when we look at one gene, you've still got 39 million plus to look at. So you're not going to answer the question by looking at a gene at a time. Also, as you can see, an individual, you, have 3 to 4 million common variants that are important to you. An individual carries 200,000 to 500,000 rare variants that are related to your clan. And again, this is why the single gene doesn't work, because some have a very low effect size, like the ACE performance gene, the ACTN3 gene, or the FTO gene, because 20% of you in the room have the right performance genes for speed and endurance, but 20% of you have. What about the rest? And in terms of the other extreme, for the BRCA genes, for example, very, very rare, 0.2% of the population, but if you have it, you have a problem. High effect size. And the kind of implications, what I've already told you, but let's go back to the bottom just because of time, that genes for obesity or genes for sprinting or genes for trainability is not going to be down to one gene, but multiple genes putting them together. And it brings me to the last point in terms of complexity, is that only 1.5% of the human genome actually encodes for proteins. 98.5% doesn't. We just think it was junk, but now we know it's not junk. It's actually creating systems that allow those 1.5% of the genome to be switched on where you want them to be switched on so that you can have the treatment benefit you want. And this is what I've tried to say in those 10 seconds, the implications you can see here. Because it's things like epigenetics that are going to be influenced by your trainability, your rehabilitation programs that you're using. That's why some improve better than others, because some do treatments better than others. So in other words, the genome is not a fixed program that I thought initially when we started this work, but a responsive system continuously shaped by life itself and what you do on a daily basis. But what you really want is to get to the individual response, which is what we are talking about. That clock is going too fast. Okay, so we need to have what we call multi-omics. Because it won't only be at the genomic level, but at the proteome level, at the metabolite level. As you can see, it's combining all of these areas together, not just your metabolite of interest or your protein of interest. And again, that's why I've gone to Asia, because there we have, like some other places around the world, but especially there, the ability in the same experiment or the same clinical trial to look at all of these things at the same time. And a very powerful bioinformatics that pulls this together, AI. But we're not talking about ChatGPT AI, we're talking about AI that integrates all of this. Which brings me to what all of you in your clinics must be doing, the P4 vision of health, which comes from the godfather of systems biology, Leroy Hood, who coined these 4 terms which you have to be using in your clinics. They are vital. Predictive, preventative, personalized, and participatory. If you're doing this, then fine. If you're not, that's what I'm saying. This is so very important, and you're going to need a combination of all these approaches to do that. Because what you want to do is go from the population or the people coming to your lab or to your clinic and identify who's a responder to your treatment. The electrical stimulation I heard earlier on, for example. You want to do personalized medicine, personalized prescription, and stratified medicine. That's what you want to do. So what I would contend is most of you in the room, and not to offend or insult anyone, is you've been doing excellently well the top left-hand side, the traditional methods. But how many of you, put your hand up, are doing the right-hand side? And then how many are putting the whole thing together with bioinformatic approaches? And then if I had more time, how many are using wearables and technology that can measure these things every day so your patient is participatory, as the P4 model will tell us? And that summarizes what I've just tried to say. How many of you doing this? And you can see from the quote at the end from Leroy Hood, the future of health is participatory, data and people in dynamic dialogue, where you're learning and you're improving the treatment you're giving your patient from data you're getting from your patient in the real world in real time. Which brings me to the fact that we have to move from a kind of reductionist view to a completely open box view, from code to networks. Because when I started off in this field 20, 30 years ago, we thought this way: DNA, RNA, proteins, that's it, easy, go home. It didn't work. What we need is to understand that 95% or 99%, that interaction, those systems, all the kind of things I've been saying. Because DNA itself, going straight down to what Dennis Noble, in the UK, the godfather of systems biology from Oxford, said, DNA does not program anything. Life emerges from networks of interactions. So the left-hand side is what we thought is the case, but actually it's a combination of all of these, this crosstalk, these feedback loops that are going on, that we have to quantify to do precision medicine. Again, how many of you are doing this? Because you want emergent functions like adaptations, recovery, performance, to make sure your protocols are working. This is what we need to do, all of us. Which brings me to the role of artificial intelligence, because this is all too big to comprehend. Our brains, however amazing, cannot deal with so much information. We need help, the role of AI, because there's data overload. And how to differentiate the garbage from the good? We need support, we need AI. Which brings us to the 5th paradigm of science, because normally we've done empirical, we've done theoretical, we've done computational, data-driven. But now we need AI to integrate all of this data and let the systems learn while integrating the data. So the power of AI comes through. And that's what it'll look like, the human-machine interface, which all of us should be doing. By the way, if you're not doing it here in your labs, I can tell you, come to visit me in Hong Kong, I'll show you this is happening, so you need to catch up if you're not doing it. Brings me to the last one here, the future from code to care. Because, as you heard before, participatory is important as well. We need to move on from just the genes, as I said before. We have to become predictive, preventive, personalized, and participatory, as I've mentioned. Incorporate all these different technologies, because genes set the score, the boundaries, but lifestyle plays the melody and AI conducts a symphony. So you need all of that to make your treatment personalized, or you're just doubling with that 20%. And I don't have time to use my examples, I have a minute and a half, but I work in anti-doping, and anti-doping is a big problem, or drugs in sport. Only, as you can see, 1% are being caught, prevalence maybe as high as 73%. So in my lab, I have a system that goes from sample to report in hours. We can look at every single gene that's switched on, add the phenotype of interest, or collect the sample easily. So my interest is in anti-doping, yours is in precision medicine. The same platforms, these are the things we need to do, as an example. And use AI to predict who's on drugs and who's not, and let the system learn about what drugs athletes may be on. And based on data, real data, not just general data available on the internet, we also have to do the experiments in the lab. I have another minute. And use the data, as we published previously, as using real data, not just what's available. So we mustn't forget experimentation, because 50% of data that all search engines use are wrong. We just don't know which 50%. And then, very briefly on technology, I want to show you here how we're trying to, in the Olympic Games, in mass events around the world, use AI to predict who's going to collapse from exertional heat stroke or not. Here we have hundreds of athletes, fully instrumented. You'll see on the bibs change from green, orange to red, and the risk of them collapsing on the right-hand side as the color code changes. Try and put all of this together, and it summarizes my 7 steps that I showed you before, and again, forgive me going so fast. But also because I've done most of my work on sports genetics, and I'm often asked, and the title I was given, which was nature versus, and I don't think versus is the right word, it should be nature and. But in terms of sport, and together with Pitsiladis Christouras, we published this paper some years ago, showing that true elite athletes are built, but only from those born with innate talent. Showing again the restrictions that are imposed by the blueprint, but all the rest is so very important. But now we know what to do and how to quantify it. So my time is up, and I want to thank Pitsiladis Christouras, my Olympian student, another student next to her, are the ones who helped me put this talk together and who have worked on some of the things I spoke to you today. Thank you for your attention.